Okay, in this video I want to walk through an old examination task. That is a examination number 99 and the task number 2. This deals with closed loop system where the process is given as a Bode plot. And the task has here 4 different subtasks and uses a Bode plot. I have copied this Bode plot into my OneNote here. So this is a given Bode plot in this examination. Let's start with task number A. With the Bode plot on page 2, that is this Bode plot, of course, investigate a designed P controller, just a warm-up task. Yeah. Here the P controller is given, the KC is given, and the question is how large is, with this KC, how large is the phase margin and the crossover frequency. Okay, you have to know that we have the dB value here. Let's have a quick look on the Bode plot. Bode plot has 2 curves. In this situation, we have here a magnitude scaling in dB values. On the right side, the phase scaling. You see here the 0 degree phase line. The 0 dB magnitude line is the same in this, but it's not a must that this is the same. The magnitude curve is black. Starts with a horizontal curve. You see the horizontal, the DC gain is in this region, we can read plus 17 dB. The phase curve is negative, goes down to this point. Here you see a phase wrapping step. So all values which are deeper than minus 180 are added to with plus 360, so full period, to a positive 180, and is continued here in this region. So you can read these values are not the actual correct values. For these values, if you want to have the correct phase, then you have to subtract 360 degrees. Okay, 0 dB gives the omega d value. So this cross point, for example, this cross point would be the crossover frequency if the P controller gain is 1, which is 0 dB. So this is a process gain, and to have the open loop gain, and the Nyquist equations deals with open loop Bode plot. We have here only the process Bode plot, so we have to add the controller gain and the controller phase to get the open loop magnitude and phase curve. So we have to add the gain of the controller to this curve. For this we need the gain in decibel. So I open a calculator and we calculate now the 20 times logarithmic value to the base 10 of the value 0.3. And this is a value of minus 10 say rounded to 10.5 dB. So the gain is negative 10.5 dB. Let's make a note. That is a gain of P controller is 0.3, and we convert this into negative 10.5 decibel. If you want to have the open loop magnitude, we have to add this minus 10 dB to this black curve. So we normally have to redraw the curve. The curve is shifted completely with a negative 10.5 dB to the ground. But of course, this new drawing of a magnitude plot is rather time-consuming and not necessary. We can, in the same way, shift the Yeah, scaling up with 10.5 dB. So the new 0 dB line is 10.5 dB higher than the old 0 dB line. So the cross point with the magnitude curve at 10.5 dB, this cross point here is there. This gives the omega d value of the P controller. And if we read this omega d value here, we can say, okay, this is 0.1, this is 0.2, 0.3. This is a little bit more than half of the value. So we can say omega d of the P controller is round about 0.26 per second. In the same manner, let's look what we also need for this calculation in this task. The phase margin value is asked, so we have to look down at the same position at omega d, say here. This is the cross point to this phase curve, and the difference between the open loop phase, which is in the P controller case the same as the process phase, the difference is the phase margin. So the phase margin is minus 180. The phase margin of the P controller is exactly this distance, and we can read phase margin of case A is, yeah, if this is minus 120, this would be 60. It's a little bit deeper, so 57 degrees. In your paper, I want to see these points, and then I can see if you have done this right. So note that this difference here, this is plus 10.5 dB. Okay, so this is case A. Let's continue with case B. Okay, it is a help for me that in case B I wipe out now all these marks and so on, because we have new drawing in the same region, and then we have a mix up of my notes. So go to case B, draw simplified curve approximation of the unit reference step response. Okay, in case B, we want to have a drawing of the reference, a sketch diagram of the reference step response. We have a phase margin of around 57 degrees. This can be converted into a damping factor around 0.6 to 0.7, and an overshoot around 10%. Now, there is the possibility to have an exact calculation, exact conversion. You can find on page 33 in 2PIDT1 systems. C workbook, page 33. There is an equation. I just skipped to this page and show you the result if you want to have exact values, but for a sketch diagram that is not really necessary. I open the workbook page and then I show you with my tool what I calculate with this conversion. Yeah, on page 33 you can find the flash design. I've called this flash design. In this case, yeah, for example, in our case, we have a PIDT1 controller with a 2PIDT1 system. If we have this exact combination, then this is a calculation method. And you see here in the bottom page part, there is a conversion equation for the damping factor D. And this equation is used in my tool program WinDF C#. And if I open this and calculate this with our phase margin of 57 degrees, then we get the following result. Yeah, there are some tools. The PIDT2 equations contains exactly this calculation between overshoot factor and damping value and phase margin. If I here select the phase margin value of 57 degrees, then you can see the exact conversion is 11% here and 0.568 there. 11%, yeah, with in the C sharp, U is 11% and D is 0.5, was war das? 57. So my estimation was not bad. So if you want to have calculated values of the phase margin, then you have this value, so 10% overshoot we expect. What can we say more to the reference step response? We have a good, there was an estimation equation. The maximum, first maximum of the reference step response can be calculated around about 4 divided by omega d, and in our case omega d is 0.26. 0.26 is 0.26 times 4. This is 15.38 seconds. So say 15 seconds. 15 seconds. Round about 15 seconds. And a P controller has a control error xd with infinite large time. It can be calculated with 1 divided by 1 plus process gain at DC times controller gain at DC. In our case we have 1 divided by 1 plus, and the process gain at DC we can read out of the diagram that is the low frequency gain of the magnitude curve. This is 17 dB. This has to be converted into a factor. So we have to go to our calculator and take the following calculation: 10 to the power of 17 divided by 20. This gives 7.07, so this is 7, and multiplied with our controller gain, which is given to 0.3. So we can calculate the control error, which is this times 0.3 plus 1. This is the denominator. Inverted gives 0.32. This is equivalent to 33% error. So there's a rather large error, and with this we can easily calculate or draw a reference step response of the P controller, which needs a t-axis. Then we have here a unit reference response should end at 1. We know we have 10% overshoot, and the final value of our curve is 0.33 smaller than 1. So we end up here, I say, end up with this final value, and this should be 15 seconds. So this is a good, absolutely sufficient sketch diagram in case A of a P controller. So we can now start with the part C of this task. What is given? In part C, we should design a PIDT1 controller. Yeah, PIDT1, so the complete program. Yeah. Tn is found with a negative 12 dB method. step depth is given to 10, and TV should be found with a minus 30 dB method. So we have to work through these both methods. Then we have to find some points of the open loop phase curve, and with phase margin of 60 degrees, we should calculate all relevant controller values, and finally in D again drawing of the simplified curve of the reference step response. Okay, so for C we have to first find the negative 12 dB over decade gradient tangent point. That is a method we use, and in OneNote we have a very nice ruler. The ruler can be opened, and we need the tangent point of a gradient of negative 12 dB over decade. So we have to mark a 12 dB over decade gradient. This mark. So this mark, this gradient is defined by a point here at 0.1 and 1 decade higher, a second point which is negative 12 dB smaller. So this is wrong. Wrong. This is plus 12, so we need 1 decade higher and 0 degree point. So you see, if I draw a line between this point and that point, then we have here a 12 dB and here 0 dB, and this is completely from there to there 1 decade. So if I take a ruler going through these both points and then shift the ruler in that way that this touches my magnitude curve, then I can find the touching the tangent point. This defines frequency. The inverse of this frequency is a good estimation for our Tn value. So with this I open the ruler again. Now I move this ruler, try to find the position good enough for these points. I see the ruler has now 7 degrees, and now I shift this ruler, make a parallel shift to the magnitude curve, and here you see in this region, here we have a tangent region. I make a green line now with my OneNote, gives the tangent curve. And yeah, the tangent point is not so easy to find, so we look for the middle point as the tangent region. I guess this is a good, say this is omega 12. Omega 12 is rather in the middle between 0.1 and 0.2, so we can now note omega 12 with the green mark is around about 0.15 per second, and our estimation for Tn is then the inverse of this. Is 1 divided by omega 12. This is 1 divided by 6.7. Let's stay at 6.7 seconds. Okay, this is the negative 12 dB method. Now I go to the diagram, and now we need the same procedure, but now with a different gradient, with a gradient negative 30 dB. So I make a point here in red, that is 10 dB, and then I go 1 decade higher and 30 dB deeper. This gives a second point. So the connection between these points go down to minus 30 dB over 1 decade. Yeah? Minus 30 dB over 1 decade. So I open the ruler again, try to fix this ruler through these both points, and I found this should, a good indication is 17 degrees. That's move this a little bit too steep, but 16 is good, I think. Oh, not steep enough. In OneNote, I can only change the the gradient in 1 degree steps. So I think accurate enough. Now I shift this to the tangent section. You see here, this ruler now touches the magnitude curve. Oh, no. Now I make a red line. Remove the ruler. This is the, you can say, negative 30 dB over a decade gradient, and in green, let's mark this. This is negative 12 dB over a decade. So the red tangent point is, we can say, roundabout here. I think a good estimation. Let's stay here at this point. This is omega 30. Omega 30 is 0.3. So we can say omega 30 roundabout 0.3. This leads to a TV value which is roundabout 1 divided by 0.3. This is 3.3 seconds. So now we have found Tn and Tv, and now we can go to the next step. What do we have to do now is we have to add the controller phase. Controller phase to phi process. So this gives then, open loop phase is phi c plus phi p. Phi p is given in the Bode plot, and phi c can be calculated. The phase of a PIDT1 controller is negative 90 degree plus arc tangent omega times Tn. Tn is 6.7 without units, plus arc tangent omega times 3.3 minus arc tangent omega times TV divided by step depths. TV divided by step depths, let's write it down, TV divided by step depths, and this can be calculated to 0.33. So we have to calculate some points. The region where we have to calculate this is where, so we have to go back now. Region. We have to read that we have to find now the phase margin of 60 degree. That means we use a cross point of the new phase curve around in the minus 120 region. So you see here the phase curve with the P controller phase crosses in minus 120 at between 0.2 and 0.3. The PID will have a phase which is a little bit more positive, caused by the differentiator. So we expect a phase curve around here, so we need some values around between 0.2 and 0.5. Omega around 0.2 to 0.5. So we make a table with some values of omega, 0.2, say 0.2 and 0.4, calculate phi c, or read phi p, or better, calculate phi c, and the addition is phi o, and check where phi o is lying, and then we can check if we need another point to calculate. So phi P at 0.2 process phase, here this value at 0.2 is rather accurately one division. We have 5 divisions, So each division is 4 degrees. So this is negative 124. At 0.4 we have this value. This is 2 divisions under minus 160 is minus 168. Minus 168. Now I calculate phi c with my calculator. Ja. Ups. Das war jetzt nicht gut. So now I use this simple calculator with a calculation with a programming unknown x. So we get this equation, minus 90 plus arctangent, inverse tangent, omega, I call it x, multiplied with 6.7, close parenthesis, plus arctangent, x times 3.3, close parenthesis, negative arctangent x times 0.33, parenthesis closed. And now with the unknown x, I have to go to calculate with x 0.2. I get 172, kann nicht sein. Calc 0.2. Oh, sorry, I have to check. It's a little bit too large. Sorry. Okay, I have forgotten this is minus sign. So the rest is okay. Now I calculate 0.2 and this gives negative 708. Say negative 7. We round to 1 degree. Negative 7. We subtract 124. No, we want to use this equation. If I do any other steps, then this equation is deleted. So I think I calculate now this is 0.4. 0.4 and say yes. Then we have positive 25. 0.5. Calc 0.5. 32. 33. And so on. So with this I make some new points in my diagram. You see the calculation can be done without calculator. This is negative 131 and this is negative 68, 60, 43. If I make some points, negative 131, a point, yeah, 131. I think I have read wrong values. That is 104.24. Sorry for this error in reading this value. This is 04. So this is wrong. This is negative 111. You have to be careful. Yeah, okay. 168. Das glauben wir. So at 0.2 we have negative 111. This is 4, 8, 11. I think this is a good point. At 0.4 we have negative 143. 143. So it could be a good idea to calculate a value around 0.3, where the FC 0.3 FC is very good, negative 140. And my calculator carries the equation. What's das denn? Carries the equation. So calculate with 0.3 gives plus 12.6, so plus 30. And we have negative 1 sorry 127. Get the point? Negative 127, 120, 28 here, 27 at this. So you can see with hand drawing is accurate enough to get a very good cross point here. And this is the phase margin value 60 degree, and this gives then the omega d of case C, and omega d of case C, omega dc is round about 0.25 per second. Yes, in my preparation I have 0.24. That's I think that's okay. So the final calculation we have to do is now the kc value. No? Look for the task. We have now derived, calculated Tn with T and Tv with our tangents, omega d with our phase curve, and now kc is missing, and kc comes again with the open loop magnitude at omega dc value must be 1. So we have to look into our equation. Omega c at omega dkc multiplied with fp, the process magnitude at this frequency, must be 1. This comes out of the curve, so we have to go now in this gradient, maybe with a ruler, vertical to this point. We see here a cross point. Here is the crossing of the magnitude curve is 10, I think 11 dB. I read 11 dB. 11 dB. No. And 11 dB has to be converted into a factor, otherwise we should calculate this in dB. So 11 dB is, now we can delete this equation, 10 to the power, where is it? There, 10 to the power of 11 divided by 20 is 3.5. 3.5. So that we can say, and FC magnitude of a PIDT1 controller is calculatable with the following gain equation. Is Kc now 3 times Pythagoras omega dc Tn squared, Pythagoras 1 plus omega dc times Tv squared divided by omega dc times Tn times Pythagoras 1 plus omega dc times TB divided by step depth squared. So if we put now all equations together and solve this equation to Kc, then we can calculate Kc is, so we have to bring all these on to the other side. We have to divide with 3.5 is 1. Kc 1 divided by 3.5 from the process phase, and then multiplied with omega d is 0.25 times Tn. This comes in the numerator 6.7 times square root 1 plus 0.25 3525 times TV over step depth. The TV over step depth is here 0.33. Now divided with these expressions, divided by 1 plus 0.25 times Tn, 6.7 squared, 1 plus 0.25 times 3.3 squared. And if we calculate this with my calculator, then we get the following result. Let's start here with the top region, 0.25. 0.25 divided by 3.5 multiplied with 6.7 with this. So this is 0.478. Store A, this is A times square root 1 plus 0.25 times 0.33 squared. This is square root, and this is times 0.3 star B divided by 0.25 times 6.7. Now I'm here in this region. 6.7 is this, squared is this, plus 1 is this, square root, square root of ans is this, so this is 1.95. Let's store in C. And finally we have here the last expression, 0.25 times 3.3 is this, squared is this, plus 1 is this, square root of ans is this. 1.3 store D, 1.3 is D, and if I put all things together, then we have shift A times recall B divided by recall C divided by recall D is 0.899, so 0.19. In my solution I have 0.2, so it's very near to my result. So these are the final values, and I think now we are ready. Last point, is the XD control error of the reference step response is 0, caused by the integrator. The Tmax time is roundabout 4 divided by omega d, is roundabout 4 divided by 0.25. This gives 4 divided by 0.25 is 16 seconds, and overshoot U is roundabout 9%. So if we draw this curve, reference step response of the PID control loop, then we can say, okay, the final value now is correct. It's 1. This time is 16 seconds, not really much faster. And here we have 9%. And you see the overshoot is the same, the time is the same, but the accuracy is much better. So the speed decrease of the integrator is compensated with the speed increase of the differentiator. So this is finally the result of this task. So I think this helps a little bit in working through these tasks. Thank you.